Today we're going to talk about mathematics for computer science. This is a series of lectures, and this book taken as some summer class for MIT, and we're going through that. What's about what we're going to talk about? I think that it's important to say that mathematics are based on some kind of proofs, a mathematical proof. So we're going from the meaning of a proof that can be from the less exact sciences. It can be analogy, it can be some axiom, it can be some agreement between experts. But when we come to the rigor of mathematics, a mathematical proof must be logically demonstrated. But we have to make some assumptions that are called axioms. And these axioms are something that is believed from us. We believe that these axioms are true, and they are part of some structures that can be true or false, which are called propositions. Propositions can be true or false. Predicates are made about propositions. Predicates are some things that are said about the propositions. Propositions define the universe, and predicates make some operation about them. Then we learn how to prove something. To prove that A implies B. How to prove that A, if and only if B is true or false. Then we go further and prove by cases and contradictions. We will know when a proof is good, when it's very, very precise. So here we go. We're going to the details now. We're gonna go through this. Yeah, we got it. So we were going to define a proof. What's a proof? Don't think about mathematics only. You must think about the proof. When you prove something, you make some judgments. You try to prove your point. You try to prove your ideas. But how do you do that? Well, first, in order to state a definition of proof, we have to go beyond that. We have to go through prepositions, which are the basic language from a proof. A proof is based on prepositions. That's how it could be said. And what's a preposition? It's a statement. It's something that communicates some idea. And it's a statement that communicates something, but specifically, being a proposition makes it communicate some truth or falsehood. For example, what of the following statements are propositions because they are true or false? These are a true statement and a false statement. That makes them propositions. So propositions are excluded from questions that imply some sort of propositions, no, some sort of statements more ambiguous that indicates some sort of abstraction that is in a higher level. It also excludes statements whose truth varies with circumstances such as it's 5 o'clock or the stock market will rise tomorrow. Because they are communicating things, but they are not saying if something is true or false. Unfortunately, it's not always easy to decide if a proposition is true or false. It's not always easy. You have to prove that. Um, then we're going to this proposition. For every non-negative integer, this is a more elaborated proposition. For every non-negative integer n, we're defining a universe. Um, well, this is called a quantifier, but we're going to go through that sometime. The value of n squared plus n plus 41 is prime. Well, this is a statement that could be true or false, so it's a proposition. A prime is an integer greater than 1 that is not divisible by any other integer greater than 1. For example, 2, 3, 5, 7, 11 are the first 5 primes. Let's try some numerical experimentation to check this proposition. Let now we're talking about a function Pn b n squared plus n plus 41. So we're going to prove, and this is true until we come to 40, because 40 squared plus 40 plus 41 is 41 squared, so it's not a prime anymore. So this proposition is false. That means that sometimes our intuition is not reliable enough. So that the main point of this paragraph is to say that a claim about an infinite set can be checked by a finite set of its elements, no matter how large the finite set is. That means you can prove some infinite function, testing just a part of it. Because it could work well until some point, but maybe you just get comfortable with that. But here it doesn't work, so you can't prove numerically. You must go through that analytically, and that's analytics is something more advanced, but it's not hard. By the way, propositions like this about all numbers or all letters of some kind are so common that there is a special notation for them. So we're going for every integer n that is far from natural numbers, p of n is prime. Yeah, and this has been proved false. Here we go through some another proofs. This is an expression from Euler. Everyone in the 18th century thought was right, but it turned out to be false, proved by Nomics 200 years after the proposition by Euler. Here are two more complex propositions.